Hello, and welcome to Chapter 10 Hypothesis Testing about Proportions. Today's lesson is going to be building on Chapter 9's lessons. If you have not watched anything from Chapter 9, you should do so now. Also, if you haven't watched any of the Chapter 10 intro or the introduction to inference, you definitely should do those as well. So let's get into it. We're still talking about proportions, only now we're going to be talking about hypothesis testing. So the difference is you should be thinking of this as like a test, not like a test you take, but more like a investigation where you maybe test some chemicals and see whether or not if they come out with the, correct formulation or something like that. That seems very unbusinessy. Let's do something businessy as our leading example as to what we're up to.
So below I have some data from the Dow Jones Industrial Average under a more than the year of times that I'm going to be looking at. So from 1982 to 1986, the Dow Jones Industrial Average was treated as a bull market. If you don't know what a bull market is, it means it was overall increasing, and we were seeing more increases than ever, at least in the opinion of the market. So I'm hoping you look at this and notice I gave you a little bit of a wider time frame than what we're going to investigate here. But I want you to see, as you look at this graph of the stock market, it's got a lot of upsies and downsies. It's very sharp looking. There's a lot of randomness. It either randomly goes up, randomly goes down. It's very unusual in behavior, but you can see overall for this time period particularly, we have more increase than we do decrease. There are some phases where it goes through where it decreases a lot, but overall the trend is up. Now, if we were to smooth out the bumpy parts of this line and look at the overall trend, you could also think of it as being up. When I say trend, I mean overarchingly, majority of the time it appears to be moving from the if you move from the left to the right, it seems to be going upward, which would mean it has an increasing trend. If you'd like to see more on smoothing, you should study time series. So what we're going to investigate is the Dow just as likely to move higher as it is to move lower on any given day? Is it going to move up equally to as much as it's going to move down compared to the previous day? So in looking at these 1,112 trading days in that period, so just the period we just saw the graph of, 573 of those days were increases. So I wrote out what that proportion is. So to find sample proportion, remember that's just your successes out of your total number of trials. And that's about 51.53%. I am rounding here. So you got to ask yourself, is that really more up days than down days? That's pretty close to 50%. Is it far enough away from 50% to be like surprising or shocking or evidence that it seems like, well, that's just not true? These two don't really seem to be as equally likely. Is it? It's not equal. Clearly there's more ups than downs. I mean, it's clearly increasing more than it is decreasing. Or is it the case that, that 51% is just caused by random chance? It isn't really that far from 50%. So as you're looking at this, you should be thinking, oh, I'm judging a distance and whether or not it's unusual. This is very much going to be related to the idea of what a z-score is. Remember, z-scores are, well, if you don't remember, I'm going to tell you right now, and you can go ahead and skip this slide if you're not sure. A z-score we think of as the number of standard deviations R value, or A value, I'm just going to write, is from the mean. So if we think of the standard deviation as like how wide a measurement is, then the z-score is the number of ticks on the ruler you've moved. So if you think like your standard deviation was like an inch, then looking at a z-score for a particular measurement would be the number of inch marks you've moved on a ruler. So it's how far you manage to move away from the mean. And it's positive if you're above the mean and negative if you're below the mean. Now let's talk about hypotheses. Hypotheses for us are going to be things that we can test, a claim that we can investigate and decide whether or not we have evidence either for or against. So be thinking this is like an investigation. I'm trying to determine if I have evidence of what's going on here. So what we're going to test is, are the daily fluctuations equally likely to be up as they are down? So we're going to assume that it actually is 50%. We're starting out with this assumption to see if we can gather support for this assumption or non-support for this assumption. So in the other words, we're going to be starting with the idea that the proportion of days in which the Dow Jones Industrial Average increases is actually 50%. This is called a null hypothesis. Okay. So we write this with a little h with a subscript 0. Now, that really isn't all that important as it is the phrasing that goes with this. What it's really doing is it's specifying your population parameter. It is saying, yes, I think my starting proportion is actually 50%. So look down further. I'm looking at this guy. This is what's more important of what I'm looking at here. I'm wanting to say, I think the Dow Jones Industrial Average, on average, goes up 50% of the time. That's what this is doing. Again, look at it. It's about a parameter, not a statistic. It's about population, not sample. So this should look very similar to when we were talking about confidence intervals, where we were investigating, oh, I want to be able to say things about the population, not the sample. So we're going to start with the null hypothesis. This is the thing we're going to assume is true. So be thinking null, that's nothing. As in, it's really not all that interesting, other than it's a starting place. What we're really interested in what's called the alternative hypothesis. This is also known as the alternative hypothesis. Now, when you look at the alternative hypothesis, we're going to be thinking of this as like, I just wrote the same thing twice. I meant to write research hypothesis. I am sorry about that. The other name it's known by is the research hypothesis. Research. My pen's doing terrible today, as always. Woohoo! So, research. This is the thing I'm trying to investigate. Yeah? This is the thing I think might be happening. So if you put on your investigator hat, you should be thinking to yourself, what's the research hypothesis? Well, it's what my investigation, like my investigator instincts, or my I'm playing Clue, I think it is. Is it Colonel Mustard in the library with the wrench, or is he in the hallway? I don't know, but I suspect that this is what is happening, really. So if you're trying to picture what's going on, here's a sort of more physical example for you besides the Dow Jones Industrial Average. In the early 90s, the proportion of students that were of non-traditional age, so 25 or older, was around about 22%. But that's a while ago. It's probably not that value still. It's probably actually higher than that because a lot more people are going back to school. It's become a lot more popular than it used to be, and any age group. So because of that, you would say, oh, well, I don't think that number is true anymore. I think it's actually higher than 20%. Or was it 22? Oh God, I got to keep track of what I'm saying. So you think it's actually higher. I want to see if that's actually true. I should gather some evidence, some more current data, and compare it. That's an example of something you can do with a hypothesis test. Another thing you could do would be like, look at my customer bases. I could see that I receive a large proportion of my sales from the November to February months. It appears that that's the majority. Is that still true? Is that proportion still the highest? I could investigate that using a hypothesis test. My null would be those 3 months have the highest proportion, and then my alternative would be I suspect that that's no longer true. So it's a way for you to check historical values in business, and it's also a way for you to check whether or not just a claim in general made by somebody is true. I keep saying true, that's a mistake. Okay, so what would it take to convince you? What would it really take for it to be not 50%? Well, you'd need to gather some evidence to show that it was higher or lower, that it was different. So we want to gather some evidence and actually figure out just how likely is it that it's different, that it's something higher or something lower. So what we've seen so far is looking at our sample, about 51.53% of the days, are increasing. The sample size is 1,112, which is big enough to satisfy the success failure condition. I hope you see where I'm going with this. And we suspect that the daily price changes are random and therefore independent, aka anyone who tells you that they can model the stock market is probably a crazy liar. Okay, so what am I really doing? Independence? Oh, a sample, a p-hat, and I passed the success failure condition? I don't know about you, but this is super pointing towards a sampling distribution. Wonder how we're going to use it this time. The sampling distribution is secretly the hero of stats too. Okay, so if we assume that the Dow increases or decreases with equal likelihood, so we're starting with the assumption, going with our null hypothesis, think null is just starter, not really all that interesting, nothing going on here, standard modus operandi guy. It has the mean 50%. So we're starting using that null hypothesis. We're going to use that to build the model. So We're going to figure out what our standard deviation is. Again, be thinking, I'm using my null to build the model. So I'm going to calculate my standard deviation using the model. So I'm going to be using 50% in here. So PQ divided by N, take that square root, not new. All right, we've got the mean, we've got the standard deviation. Let's go ahead and use that model to look at different things. Well, to try to investigate, I should say. So why standard deviation, not standard error? Harkening back to chapter 9, remember when we're using the standard error, we're just using sample stuff. And when we're using the standard deviation, we're using population proportions. We're starting with the assumption with hypothesis testing that the null tells us what the population parameter is. It says that it's 50%. Because of that, I know what the parameter is. That's what I'm assuming it to be. Now, that might not be a good assumption. It might be bad. We'll find out later when we talk about error and power in chapter 12. That'll be fun, I hope. Maybe. I always found power kind of interesting. I guess we'll see what y'all think. Okay, so, hey, I'm not really... That was my bird, I'm sorry. I'm not really doing standard error. I'm actually doing a standard deviation because I have a parameter, not a statistic. Cool. So we asked ourselves, how likely is it that I got that sample that I did, given that the null was true? So we're really asking, just how unusual is 0.5153? It doesn't look very surprising. If you're wondering why I say that, hey, look down at this graph. There it is. So I've placed on here our null hypothesis, our p-value, our mean. So as you look at this, be thinking, oh yeah, that's the mean of my distribution, which came from our null, which happens to be the value of p, because this is a sampling distribution. Its mean is the center, which is also the parameter, which is the population proportion, which in our case we assume to be 50%. And then remember, my spread was about 0.15, so if you're looking on here, I've included the 68, 95, 99.7 rule stuff. And then I've placed on here a ticker marker or a little flag where 51.5% lies. And then I want to ask myself, how unusual is that? Well, I'm going to calculate some probabilities. So first I'm going to find the probability, how big it is over here. What's over here? Well, it's the fact that I got my sample p hat or something greater. So I'm looking at the things greater than the p hat value I got. Additionally, I'm also looking at the values over here, which is the probability that I got the negative version of that p hat. So be thinking using symmetry going the other way. So be thinking like the stuff smaller than my negative p hat. Why am I using the negative and the positive guy? Well, I started with the assumption that the mean or the p-value or my p hat, sorry, not my p hat, my center of my distribution is 50%. But my alternative is I want to know if it's different from 50%. So is it bigger or is it smaller? So the blue half of p hat action I've got here is the assumption of, oh, is it bigger? And then the negative p hat action over here is actually the question of, is it smaller? So there's two areas I have to account for. If I was just looking for bigger, I'd only be looking at the greater than one. If I was looking for less than, I'd be looking at only the negative and less than one. So I'm going to calculate these probabilities using just standard normal means. So using a calculator computer program or the normal table, you can pick your favorite one. Woohoo! We can find that the exact probability is actually in both those pieces 30.08. So I've sort of specified down here in the lower paragraph. Really what happened was I looked at what percent of days are above 51.53% and which ones are down or below that, and they're both 15.4. It's symmetric, so then you know, it's not surprising they end up being the same. So you really could have taken and just done one of them and doubled it and coming up with 30.8. So now you got to ask yourself, is that unusual? That seems pretty not unusual. That's happening like 30% of the time. Closer to 31% of the time. Not unusual at all. Okay, so we started with the we started by assuming that, hey, it's actually 50%. Then we looked at the data. We got some evidence. We made this assumption that, hey, it's probably 50%. Let's see what's going on. And then we gathered evidence, and what we want to do now is we want to make some sort of conclusion. So the analogy we use for this is the logic behind the British common law system. If you know anything about the common law system, it's the laws that Britain originally had in the United States when they came over in the colonies. If you don't know anything about the law system or the legal system, I have another analogy for this involving the story behind The Boy Who Cries Wolf. But hopefully this one will work for you, and then we don't have to worry about me telling you 400,000 stories. So the idea is, under British or the common law system, you get charged with something. Oh no, that's bad. I wonder what's going to happen to you. But here's the thing. They charge you with a crime. You go through the trial. We start out with they gather some evidence. They consider the evidence and they're going to make a conclusion. And this is exactly how the null hypothesis and doing a hypothesis test behaves. So we take the evidence as facts, and we either want to, look at you and say, what happened to you? So you walk into the courtroom knowing what you've done. You know if you're innocent or not. Yeah, you're either innocent or you're not. But the judge and the jury, they don't know that. They just know what the evidence shows. And it might show or point to that you're guilty. It might show or not show that you're not guilty. So think about it this way. The jury considers the evidence, presuming that you're innocent, because that's how the common law system works. And then we ask, hey, is it plausible that we got this evidence if, in fact, the defendant were innocent? Okay. Could it have happened by chance if the null were true? Same idea. And then they're going to make some conclusions. Hey, are you guilty or are you not guilty? Be careful with this because there's a distinct difference here. The jury never declares you innocent. Uh-oh. They just declare you not guilty. They look at you and say, we can't prove you did this. Not guilty. Or, we can prove you probably did this. Not that you actually did it, you probably did. Guilty. The same thing is going to happen with the hypothesis test. We start on the assumption that the null hypothesis is true. We gather evidence, and at the end we say, it looks like this one, looks like that one. I can't even really say which one it is. Sad but true. Okay, a little bit more about evidence. So the evidence we're going to use is what's called the p-value. It's the probability of observing the sample data that you have, given that the null hypothesis is true, and that means that, oh no, if you got something low, then the data was really unlikely. So you gathered something that shouldn't happen, like not that often, and you got it on your first try. That seems like that's not so true. It really says that maybe my null hypothesis isn't the way to go. Now, when you have a high p-value, or just maybe not low enough, that means that the data, it's pretty likely. It's pretty consistent with what the model says. Your model seems pretty true. The null hypothesis appears to be showing us something that is pretty reasonable or close enough to reasonable that you just can't detect it. And since you just can't detect it, we just say that we don't say that it's not true. So we call this a failure to reject. This is a little bit strange. So what do you do with an innocent defendant? Or what do I do when I have a defendant who, they're definitely true, but I can't really prove that they're not untrue? Well, if there's insufficient evidence to convict a defendant, the jury does not conclude the null hypothesis is true. They fail to declare that the defendant is innocent. AKA, the jury can only really fail to reject, just like we said earlier. So then we declare it not guilty. And what's unusual about this is we really want to see some rejection. We want to have evidence pointing towards our alternative. I know this seems strange, but math is a strange beast, as you've already seen in your past, but we want to reject. Because it's going to point us towards some research. It's going to give us evidence of what, our nothing is indeed nothing, and therefore we can go towards something else. So if we're looking at a particularly unlikely incidence, then we're going to fail to reject our null hypothesis, aka we're going to declare it not guilty. All right, let's do something real quick. Let's do an example to make sure we understand what p-value is all about. So I'm going to go through this example after you read through this slide. So what you should do here is these are all true or false questions. I'm going to read them out loud. If you want, you should pause this video, take a few seconds to write down for yourself which ones you think are true and which ones you think are not true, and then I'm going to go over the answers. This is just a nice way to check yourself to see if you understand what's going on. The one thing I would caution you about this is it's real tempting just to look at the answers, but are you really checking your understanding if that's true? And there is one question in here that is it's just so false. It's so false, it's not even funny. So false. I mean, it's like super mega. We need false with a capital F. We need something better for this. So take a moment, pause this, read through these, and decide which ones you think are true and which ones you think are false. Okay, we're back. P.S. My pick is C. That's the one that's super mega false. But now I got to go through all of them. So remember, when you're looking at p-value, we're looking for which are true and which are false, and we're going to briefly explain why. P-value is a probability, so be careful. Probability, not proportion. It's the likelihood that something happens, not a count compared to a total. All right, so which of the following are true? Briefly explain. A very low p-value provides evidence against the null hypothesis. Yep, that's exactly what it does. It's small, which means it's unlikely, which means that that's probably not what's going on. It's contradicting what you're assuming is true. A high p-value is strong evidence in favor of a null hypothesis. This is the one you might have called true, but it's actually false. High p-value just says there's no evidence that it's not untrue. Oh, I know, so many negatives. We can continue with our assumption that the null hypothesis is true, but we can't really prove it to actually physically be true. Again, we don't declare innocence. We don't declare something true when it comes to hypothesis testing. We only say it looks like the evidence points this way, it looks like the evidence points that way. So be careful. Here's the one that's super mega false. That was too many. So a p-value above 10% shows the null hypothesis is true. True. There it is. You just declared something true. That's something we'll never actually be able to do with hypothesis testing. So that's the one you should never say. You should never, ever say that the null hypothesis is true or false, or any hypothesis is true or false. So again, no p-value will ever tell you that. So if a null hypothesis is true, you can get a p-value below 0.01. Uh-oh, you can't get one. It's saying the null hypothesis is true, assume it is true. It's not declaring it true. It's saying if it was, can you get something really unlikely? Well, yeah, this is 1 out of 100 times, so it's quite possible that you would get this 1 out of 100 times. You might happen to accidentally pull the bad sample. That happens with 1 out of 100 times. This is unfortunately false. This is exactly the problem of doing hypothesis testing. So, a little bit of a summary. Here's how we divide the hypothesis test into steps. The first thing you must do is declare your null and alternative hypothesis. In the past, I would say that this is the step that most students want to, well, skip. And if you skip this step, you might have the wrong null hypothesis, and then you go to make your model that you're going to calculate your probability on, and your center is wrong, and then everything goes wrong after that, and that's bad. The other thing is your alternative usually is the easier one to declare first. It's usually the easier one to find. And if you have the wrong alternative, you'll have the wrong p-value. This I see happen all the time. I try to find my alternative first and then build my null because the relationship is very, very distinct and always the same. So I would warn you, don't skip this step. The next thing you're going to do is you're going to build your normal model. So we're assuming that the null hypothesis is going to make our center. Then we use that to form our standard deviation. And then we can use that then to find our z-scores and go ahead and come up with what our probabilities are going to be. Just a quick warning. Hey, just because the conditions are satisfied and we can use the sampling distribution with the normal model, I mean, you should definitely check your conditions. Although I'm saying, oh, use the model, you know, it's great. You should check your conditions before proceeding because you should always check yourself before you try to use something to see if you even should. All right. Now we're going to perform the test. This is more of the mechanics of this system. If you're looking at this, we're doing what's called a 1 proportion z-test. If you use the calculator, it's literally called that. It's like abbreviated 1 prop z-test. If you end up using MyStatLab, or sorry, not MyStatLab, Minitab, it just uses a 1 instead of the word 1, a numerical 1, and then it calls it a 1 proportion test. So that's fun. There's only 1 on there, so it's nice. What we do first is we calculate the z-score, similar to what you saw me do, and then we use that to calculate the p-value, the probability. We need the z-score to calculate this probability because it gives us a cutoff for that. Beware as you look at this z-score, the usual framing we call this is we usually call it the z-statistic because it's the value or z-score coming off of your statistic that you use. Statistic. I can't believe I just had a... Sorry, I was having pen problems, then I screwed up. It's also called the test statistic. Because you're doing a hypothesis test. Yep. So those are two other names you may come across in your journeys through statistics land. Your book tends to prefer, and your homework tends to prefer, a test statistic, just so you're aware. So just remember, when you think test statistic, z-statistic, it's just a z-score. Good times, great mathematics. Lots of words and junk. Anyway, so yeah, z-score. That took me too long to talk about. Oops, I hit a button. All right. So the next part in our mechanics lesson is, let's calculate our p-value. If the p-value is small enough, then we're going to be headed to rejection land, which is kind of what we want. All right. So when you're looking at this and calculating your p-value is always determined by your alternative hypothesis. You always look at your test statistic and then determine how you're going to shade based on your alternative. So when you're looking at this, be aware your alternative hypothesis, super important here. So if your alternative was wrong in step 1, here's where it causes all kinds of problems. Oh no! I'll talk a little bit more about a common error with this when we get to an example, which is what I'm doing after I get through the last step. So again, remember, small p, that means I had something that was very improbable, because p-value is a probability. Very unlikely. Then we're going to reject the null, because the null seems unlikely. Conclusion time. The primary conclusion is the formal hypothesis test is only a statement stating whether we reject or fail to reject. Your conclusion about the null hypothesis should never be the end process. You should always make your decision not solely on the p-value. You should look at other things involved. Does it seem reasonable? I want to warn you right here, when you're writing your conclusion, I'm really looking for not only did you make the correct decision, like reject or fail to reject, because those are the only choices, but also, did you tell me the answer to the question being posed? So if I'm asking you about business practices and whether or not ethics training affects people's honesty, you should be answering about like the question like, oh yes, it appears to increase the honesty rates among CEOs at the 4% level. You should be actually answering the question. Don't just say reject, I am a robot, fail to reject. That's, I mean, I could, it's not that interesting. It's just the same like if your boss came up to you and asked, oh, are we receiving, more accounts this year than we did last year? You should be able to actually answer that question. Yes, it appears so. I did a hypothesis test and that was what my results told me. Not just reject, p-value was small. Okay, no more robots. One thing to be aware of, since you are all business students, there are some things that are going to affect your results that have nothing to do with statistics. And that's the idea that business decisions really are based on a couple different things. If your test isn't significant enough to make a difference, aka the statistical significance of the test, then no one's going to bother with it. I mean, if you're saving a penny on an account that comes up once in a million years, that's not going to matter. So be aware of that. It's got to be enough for it to matter to your company. If your difference is maybe like 3% and that's not enough to cause any big change in anything that anyone's doing, it's not going to matter. It's just like if you implemented a new training process and then asked yourself, did that decrease our rate of defects? And the answer was no. Why bother with the training process? It costed us time and money. Oh, that's the other thing involved. Cost. If the action that you're proposing because of the hypothesis test is cost proclivative, no one's going to do it anyway. So if it's a change in your production line that makes your widgets more effective or less likely to not screw on correctly, and it costs $8 million and your company is only worth $2 billion, sorry, 2 million, 2 billion, whatever, no one's going to do it because it's half the cost of the company. The other thing to watch out for is the effect size. Effect size is all about the difference in the statistics observed. This is related back to the significance of the test. So again, be thinking if it's insignificant in its change, then it doesn't matter. Effect size is all about, is the difference in what I'm seeing enough to be noticed? So one of the things you may have noticed over time, if you've ever bought Arizona iced tea, they always cost 99 cents. Always. They costed 99 cents when my mother, who is in her 60s, was buying them. How have they been doing that? Well, they just change their formula and tweak it ever so often and start to use slightly cheaper ingredients or change things and don't use advertising money. So what do? They make slight changes that no one notices. Effect size, but that causes their costs to go down. Interesting? Maybe. but the effect isn't noticed by the customer, and that's the most important thing. Yay, T. Secretly, there's other options to what we could use for the alternative hypothesis. Well, not secretly. I've already done a two-sided alternative with you. When we looked at the Dow Jones Industrial Average, we were really looking at, hey, is there a difference? Or I don't care if it's greater or less there, I just want to know if it's different, which is actually what's called the two-sided alternative. It looks like a not equal to, because it could be bigger, could be smaller. I maybe don't know which way it's going to go, but the idea is that I just want to know, is it different? Is it bigger? Is it smaller? I don't care. Is it different? Now this one had two probabilities we were calculating, one on each side. That's why we had the two tails in the distribution when we were drawing the distribution with the p-values on it for this test. That's called the two-sided for that reason. It's also called a two-tailed for that reason. Okay. Now, as far as the alternatives, that you could also have besides that is you could also have the one-sided alternatives. Now, you only get one alternative hypothesis. Don't think you need to write three, and you'll see that when I do the example next. So it could be you think things have gotten smaller. Oh, I think I've reduced my defect rate. Or you could think, oh, things have gotten bigger. I think more students are going back to school at an older age than in previous decades. Stuff like that. Now, the one-sided alternatives only have one side of probability when you're calculating them. So we're going to see that as well. Let's look at an example with a one-sided test. So suppose you have this survey, well, no, don't suppose, this was actually data. A survey of 100 CEOs finds that 60% think the economy will improve in the next year. This is from 2015, just for reference. Is there evidence that the rate is higher among all CEOs than the 55% reported by the public at large? So we're going to go through the following steps. What are the appropriate hypotheses? What are the conditions and assumptions that must be met to proceed through the hypothesis test? We're going to find the z-statistic. Then we're going to determine the p-value and write a conclusion in the context of the problem. So a couple things. Before I proceed through this hypothesis test, I would highly suggest that you try writing some of these right now. So pause your video, write down what you think these are going to be, and then confirm whether or not you're correct. As I go through the slides, you can also pause at any step and predict what the next thing is based on anything you might have changed. So the first thing we're going to do is, what are the hypotheses? I really wish this would slide in, but it won't on this type of viewer. Oh well. So here's the thing. What we want to know is there evidence that the rate's higher among CEOs? Is it higher? That's what's pointing us to, oh, I want to know, is it bigger? That leads us to the alternative hypothesis, is that the proportion is actually bigger. I hope that makes sense. So I think it's going to be bigger. The alternative is always easier to come up with first, I think. Opinion, not fact. Then all you have to do is write the null hypothesis, which is just the equal sign version of the alternative. Pro tip, the null, always an equal sign. Always. That doesn't look like a word. I hope you noticed that a couple slides back. That when I write the null, it's always an equal sign. This is only like our fourth null we've seen, so it's an equal sign every time. So I always go looking for the alternative first, and then I look for the null. The other thing to watch out for as you're approaching these is there are actually two numbers showing up on here. There is the 100 out of 60, that's right there. That's a terrible job of highlighting, good job me. And then there's the 55%. So here's where you have to be careful, very careful. One of these is from a sample, one is about a parameter. Hypotheses are always about parameters. You should look at this and be like, oh, well, it's from a survey. This is my p-hat action. This is my sample stuff. I'm not going to be using that to come up with my null hypothesis. I should be using the 55%, I almost said 15, reported by the public at large. Oh, by the public at large, so lots of people. This is a proportion about a parameter, about a population, not a sample. That's the one I should be using in my null and alternative hypotheses. Hope that made sense. Pick it apart, yo. Read carefully. I would also suggest if these are very wordy, you read them more than once, because sometimes there's a lot of little nuanced things inside them and a lot of numbers floating around. You got to pick out which ones are the ones you need. Okay. Under what conditions and assumptions can we proceed? Hey, we got to check what we got to check. So I'm pretty sure that 100 CEOs is, less than 10% of all the population of all CEOs, because that would mean there's only 1,000 in the 1,000 in whatever economy I'm doing this in. That seems a little low, so it's probably okay for the 10% condition. The next thing you should look at is, since I have 60 successes in my 60 out of 100, that means I have 40 failures. Those are both bigger than 10. We're good to go on that one. Check, check. The last thing is, you should ask yourself, was this random? There's no information about that. That makes me a little, hazy about it. These are good enough for now. Oh, it was random. Did I write that in the problem somewhere? I didn't say it was random. Naughty teacher. I gotta fix that. So, bad question. Should have written random in there somewhere. Bad teacher. I'll fix it later. Oh shoot, I'm recording now. I'm not fixing it. Hey, sorry. Let's find the test statistic, or the z-statistic. If you're wondering where the p0 comes from, this was coming from your null hypothesis, so just keep in mind as you approach finding the test statistic, you're going to be using the null to find your standard deviation, and to find your test statistic, that's the values that help you make the model. So we just do some calculations. Be careful, make sure you actually physically calculate this at some point. Using your calculator, make sure you get the same numbers I do. If you don't, give me a ring or send me a text or send me a remind message, because, well, we need to talk about how to enter things into the calculator to make sure you can enter them in correctly and get the correct result, which, this one's a little complicated. So here's calculating our p-value. As you look at this, there's an important thing to notice. This is done using either your tables, your calculator, or your Minitab. When you're doing Minitab, you won't even have to calculate the z-score, but one thing to note is, notice where that arrow is pointing. That's coming from the alternative hypothesis. Since our hypothesis was that we think the CEOs were greater, we are looking at, is it greater than my test statistic? That's where the alternative is getting used. It's telling you which way to shade. So if you have your alternative incorrect, this will be incorrect. How much will it be incorrect? Well, if you end up with a p-value that's 2 times what it should be, you used a 2-tail when you should have used a 1-tail. If you end up with an alternative that's half of what it should be, then you used a 1-tail when you should have used a 2-tail. Just keep that in mind. Let's write our conclusion. With a p-value of 0.172, that's pretty large. So the data collected, not unusual, as we already said, so I'm going to be failing to reject my null hypothesis. I can't say that it's not true. My evidence seems to point towards it, actually. So I would say there is no evidence that the proportion of CEOs who think the economy will improve next year exceeds 55%. You could even say in there, it appears that the CEOs agree with the public at large. It looks like they think it will be about 55% as well. There's a couple different ways you could phrase this, but really what we want to say is something that answers the question and points towards the null hypothesis, just like the evidence does. We also always mention the evidence and the fact that we can't really disagree with this idea. We're not saying it's true, we're just saying where the evidence points us. Hypothesis tests are particularly useful when you're trying to make a decision about a parameter. So whenever possible, we're going to also try to do a confidence interval, because confidence intervals are going to give us good estimates of what the parameter actually is. So be aware that although you have the hypothesis and it's going to point you towards one way or another, it never declares the truth. It never tells you what the value actually is. If you want to know what the value is and actually estimate it, you should be using the confidence interval. So I hope you're wondering, oh, she said small p-value, large p-value. How small is small enough? How large is large enough? Usually, we use something specific to try to decide that, and that's called the level of significance. And it's sort of context dependent. So alpha level is also called the level of significance. And this is where statistics takes a very interesting turn. Here's the thing. For statisticians, significant means something specific. For you, when you're reading something, you might think, oh, well, my parents have had a significant impact on my life. My significant other is significant to me. Those are more of English or personal definitions of what significance is to you. To be significant in statistics, you got to be less than whatever alpha is. So what do I mean by is significant? Is small. So we call values significant if they're less than whatever alpha happens to be. Fish symbol, good times. So you should be asking yourself, you still haven't told me what alpha is. How small is small enough? Well, most commonly we use 5 or 1%, but there's really no steadfast rule. If you want the actual definition of what most people use, it's usually 5%. I've seen someone use 10% and even 12%. I don't know why they picked 12. They just did. It was kind of crazy to me. But more often than not, we use 5%. And generally, this is the one approved by the Statistical Association of America. That's not their name anymore. I just got their name wrong. The American Society of Statisticians. I'm not remembering the name of this place. The people who decide what we do with stats, those guys, they usually say if you're not sure, use 5%. So if you're not sure, that's the alpha value we're going to be using. We're going to use alpha is 5%. So just keep that in mind. So if you ever are doing a question and they don't give you a particular significance level, you should be using 5%. But again, this isn't a steadfast rule. It changes all the time. So, you know, there's the modern standard for your anything. When you're doing your conclusion, you should always accompany your test with the p-value. What I mean by that is you should declare not only why did you make your conclusion, but what value caused you to make that decision. So really what that does is it allows anybody who's reading your information to detect whether or not you made the right decision. It also tells you people that if later on we decide to change what the standard is, what the p-value is and whether or not they should agree with you or disagree with you based on updates. So as you look at this, your reporting your p-value is very important because it strengthens your argument about why you either rejected or failed to reject. People who don't report their p-values are usually up to something. You should be suspicious of those people. Let's move on to the summary. Oh my gosh, what can go wrong? Don't base your null hypothesis based on what you see in your data. I have seen plenty of people look at their sample, say it's smaller, and decide it's smaller. Smaller doesn't mean anything. It could be caused by random chance or just variation in the sample, also known as sampling error. So it could be you just happen to grab a slightly smaller sample than somebody else would have. Don't trust just the sample to tell you what's going on. Do a hypothesis test. Don't base your alternative hypothesis on the data either. If you're looking at your data first and then making your decisions, you're probably not doing proper scientific research and you're probably not doing your statistics right either. Don't make your null what you want to show to be true. Your null is nothing. It means nothing to us. It's the status quo. It's the guy we don't really care about. It's the alternative that we're interested in. The null is just some statement about equality. It's not going to tell you if it's smaller, greater, or different. It's just going to tell you what it is, which isn't that useful. Don't forget to check your conditions, also known as check yourself before you wreck yourself. Don't sort of solidify yourself on arbitrary alpha levels. I know I just talked about this a couple slides ago, but you do use 5%. But if your p-value is like 0.051, it's only slightly bigger, you could probably still make the same decision and be okay. The same thing for 0.049. I know a lot of you have asked me on occasion, and I've gotten other students ask me on occasion, if I round this, does it make a difference? When it comes to making probability tests, you are the end-all be-all as to whether or not you think that is significant. If you decide that it's significant, be loud, be proud, support your information, write your p-value down so that other people can either agree or disagree with you. And it's okay to disagree. It's just do it on a scientific level, not a personal level. And don't confuse practical with statistically significant. Just because it's significant to you doesn't mean that it's going to do something practical for your company. That doesn't mean you shouldn't use statistics to make decisions. You absolutely should, because sometimes they're going to inform you of lots of different things. One of the reasons why we have the ADP program now at Northwood is because people in the recruiting office noticed that our percentage of adult students was increasing. It was changing. It was different from what we'd seen previously. And so we got into that niche market of, oh, how can we appeal to adults? So keep that in mind. What have we learned? Summary time. So if you don't like summaries, you can go ahead and stop this video. You're done. Woohoo! So what did we learn? How to formulate hypotheses. Remember, null, nothing, what's going on. It's your standard. It's what you're using to build your model. Be able to perform the hypothesis test in detail. Start with your null, come up with your model, build up, find that test statistic, get your p-value, make your decision. Speaking of p-values, a p-value is really estimated to tell you what's going on. So be thinking to yourself, what is my p-value telling me? It's really all about formulating the correct hypothesis, assuming the null is true, and then using the alternative to point you in a specific direction. So a small p usually doesn't support the null hypothesis, pointing towards the alternative. A large p is support for the null, and that may or may not be a good thing. So here's the steps all put together in one. State your null, determine your distribution model, come up with your mechanics, as in calculate your values that you need, come up with your conclusion and make your decision. Be careful when you're looking at one-sided versus two-sided, and make sure you justify your decision using your p-value. The last thing to keep in mind is when you're doing your value estimating, and you should report your effect size. Now, your test may be significant but practically meaningless. Just keep in mind, just because it's important doesn't mean that it's important to everyone. I hate to say it, but some of the ideas that you will present at some point in your lives may not matter as far as value goes. That doesn't mean you should stop using statistics. You can often use it to make good decisions, but remember that. Have a good day. I don't know what I'm saying anymore.